There are forces all around us that we can't see, hear, or feel, but they have the power to change matter itself. Today, we're going to pull back the curtain on the super clever device that makes these invisible forces visible, the ionization chamber.
So, let's just start with that big question. How in the world do you measure something you can't even perceive? A silent force that can literally alter the atoms of the world around us? That's the huge puzzle we're going to tackle today.
All right, here's our game plan for unraveling this thing. First, we'll get a handle on why detecting the invisible is such a challenge. Then, we're going to build our own detector, right from the ground up. We'll see the chain reaction that actually triggers a signal, figure out how to turn that signal into real information, and finally, see where this incredible tech pops up in our everyday lives.
Okay, let's dive right in with the fundamental challenge. How do you even start to measure something that leaves absolutely no trace for our senses to pick up on? I mean, think about it. From the X-rays that help doctors diagnose us, to the nuclear energy that powers our cities, we rely on these forces we can't perceive. So to use them safely, detection isn't just, a nice to have, it's the first and most critical line of defense. It's everything.
So how do we crack this nut? Well, it turns out the solution is surprisingly simple. It's really elegant. Let's break down the anatomy of one of these detectors.
In fact, let's build one together, right now, piece by piece. It all starts with the most basic component, just a sealed container. Think of it as our little controlled environment, keeping the important stuff in and everything else out.
Okay, next up, we fill this container with a stable gas. Something like air or argon works great. Now, I want you to imagine this gas as a huge field of atomic targets, just sitting there, perfectly still, waiting for something to happen.
Now, inside our little chamber of gas, we're going to place two electrodes. There's a central rod that's positively charged, we call that the anode, and then the outer wall of the chamber itself acts as the negative electrode, or the cathode.
And for the final piece of the puzzle, we apply a voltage. This creates an invisible electric field stretching between those two electrodes. And that's it. Our trap is set. The whole system is armed, totally silent, and just waiting for an invisible visitor.
And that brings us to the action. This is the really cool part, where we get to see how one single, tiny particle can set off an event that we can actually measure.
To really get what happens next, let's use an analogy. Think of a particle of radiation. It could be an alpha particle, a beta particle, a gamma ray, doesn't matter. Think of it as a bowling ball. And all those gas atoms inside our chamber, yep, those are the bowling pins, all set up and waiting for a strike.
All right, here's the play-by-play. First, our bowling ball, that radiation particle, flies into the chamber. Wham! It slams into a gas atom with enough force to knock an electron clean off. That's ionization. What we're left with is what's called an ion pair, the atom, which is now positively charged, and that free little electron. And instantly that electric field we set up springs into action, pulling the negative electron toward the positive center and the positive ion toward the negative outer wall.
So we've had a collision on an atomic level. But how does that become something useful? I mean, who cares, right? Well, this is where we translate that tiny event into real, usable data.
This brings us to the absolute key concept, the ion pair. This little duo of a positive ion and a negative electron is our fundamental unit of measurement. Every single pair represents one countable event that was triggered by radiation. It's the whole basis for counting this stuff.
Now here's the thing. A single particle of radiation doesn't just create one ion pair. Oh no, it tears through that gas, creating a whole trail of them, kind of like a boat leaving a wake in the water. And the movement of all these thousands of tiny charged particles rushing toward their electrodes is, by definition, an electrical current. It's incredibly small, for sure, but with modern electronics, it's absolutely measurable.
And here it is. This is the secret sauce, the whole genius of the device. The more intense the radiation is, the more bowling balls are flying through, and the more ion pairs get created. This generates a stronger electrical current. It's a direct one-to-one relationship. More current means more radiation. It's as simple as that.
Okay, so we can measure it. We've got a number. But what do we actually do with that information? Let's zoom out and see where this amazing technology shows up in our world, making radiation visible right where it counts.
And trust me, the applications are everywhere. These chambers are absolutely critical for calibrating medical X-ray machines to make sure they're safe. They act as these silent guardians in nuclear power plants. They're used to precisely measure doses for cancer therapy. And hey, you might even have one in your house right now.
A tiny ionization chamber is the heart of many common smoke detectors. How cool is that?
You know, this quote from the brilliant physicist Lord Kelvin it nails the essence of what we've been talking about. Measurement is the foundation of all knowledge and control. If you can't put a number on it, you're just guessing in the dark.
So, at the end of the day, that's what the ionization chamber really does. It takes this abstract, invisible, kind of scary force, and it translates it into a concrete number we can see and act on. It transforms a potential hazard into a manageable tool, giving us the power to use radiation safely for the good of all of us.
So yeah, we figured out how to see radiation. It really makes you wonder, doesn't it? What other fundamental forces, what other unseen realities are swirling all around us right now, just waiting for the next clever invention to finally bring them into the light?